Okay. So we will refer to our training data or the entire data as D, which contains m plus n points, where you have m or rather n training points and m test points, right, or the other way around as we defined on the previous slide. Now we also know that some true function exists such that y is f of x plus epsilon. What does that mean? That yi is related to xi by some true function f, but there is also some noise epsilon in the relationship, right? Just like in any relation, that you might have some noise. So you ideally want y is equal to f of x, but there might be some minor noise, and for simplicity we assume that this noise is zero centered. That means it has zero mean and a small variance sigma square, right? So that's what we are going to assume, and of course we do not know f, right? If we knew f, then there's nothing to do, but we don't know f. So what we do is we approximate f using f hat, and then we estimate the f hat, the parameters of f hat, using the training data, which is going to be a subset of this capital D, right? So I'm going to refer to the training data as T, and it's going to be a subset of the D which I have defined earlier, and y is going to be f hat of x now, right? So that's the approximation that we have made. Instead of y is equal to fx plus epsilon, which was a true relation, and we did not know f, we have come up with some approximation f hat, and we have freedom in choosing what f hat we want to choose from like a family of functions, and we could have different parameters for that, right? So we are interested in knowing the expected value of f hat x minus f of x the whole square, right? So this is the mean square error indeed. So here expectation stands for the mean, this is the error, this is the square of the error, so this is the mean square error. So simply put, the square of the difference between the predicted value from our approximation and the true value, and this expectation computed over a large number of samples, right? That's what we are interested in estimating. But of course we cannot estimate this directly, right, because this requires us to know f of x, and we don't know f of x, right? So how do we compute this, because this has a quantity that we don't even know, right? But we will still be able to estimate this empirically, because although we don't know f, we don't know the true function f, we have been given a lot of training points, right, where these y's are known. So those y's we know are coming from some relation f of x plus epsilon. So even if we don't know what the relationship is, we are given some of these x's and the corresponding y's. So we know the x comma y pairs, right? So we have some idea of what f of x looks like for the given x's that we have. We don't know the full function, but at least for the x's that are there in a training set, we know what the y's look like, right? So we have some of these, and similarly f hat x is also we can compute, because we can pass the x through the function that we have approximated, or the approximation function that we have used, and that would give us y hat I, right? And then we could compute this as a difference. So fx you could replace by y, and f hat x you could replace by this y hat, right? This is y hat, which I often call it as just y, and it's from the context it's clear whether I am referring to f hat x or the original function, right? But now I will make it explicit that one is or I don't need to actually use y hat here. I can just say f hat x, which you understand what is, and fx is just y, which are the training points that are given to me, right? So now let's go further. So this is the quantity that I am interested in then, right? So I have just replaced f of x by y and f hat of x by y hat, right? So this is what the quantity is that I am interested in, and now I know that y is actually f of x minus epsilon, right? So I can just substitute, f of x plus epsilon, so I can just substitute that. And now I am just going to like kind of open up this square and rearrange some terms, right? So I am looking at this as a minus b the whole square, where a is equal to f hat x minus fx and b is equal to epsilon, right? So that's how I have expanded this formula. I just open the bracket, rearrange some terms and so on. So expectation of a sum is the same as the sum of the expectations. So I can write this expectation of the three terms that I had, a square minus 2ab plus b square, as the sum of the expectations of these terms. So, expectation of a square minus expectation of 2ab plus expectation of b square, right, with a and b as defined earlier, and of course, the constant I can take outside. So, now if you look at it, this is the quantity that I was interested in and I did not know how to estimate it, but now I have been able to rewrite that quantity in terms of things here, and here I see some hope now, because now I have this y hat and y here, which is just the training data that was given to me. Those are the y's and the predictions that my model made. So, this is something I can estimate. Expectation of epsilon square I can estimate, it is just the, I had already assumed that epsilon comes from the normal distribution, right. So, expectation of epsilon square is just going to be sigma square. So, that I can compute. Again here I have a slight problem, but we will come back to this, right. So, I have just now rewritten the quantity of interest in terms of a set of quantities, of which some quantities I can compute, and there is one quantity which I can still not compute, but we will see how to deal with that. Okay. So, now what we will do is, now we will take a small detour to understand how to empirically estimate an expectation and then return to our derivation. Right. So, let us see what I mean by that. So, suppose we have observed the goals scored in K matches. You are watching some football, a lot of football games, and you have watched some 100, 200 games, and you have observed the number of goals scored, say 100, 200 games between, if you want, the same pair of teams, or say at least one team is constant there, right. So, how many goals on average does say Brazil score or some other team scores, right, and you have observed this. And now the way you compute the expected value, we are interested in what is the expected value of z. So, our random variable here is z, and it can take any value 0, 1, 2, 3, 4, 5, 6, 7, I mean as many goals as you can score, and you are interested in the expected value, right. Now, expectation as you define in probability, of course, is you have to repeat this a large number of times, but you only have like some k matches that you have seen. The way you compute the or you empirically estimate the expectation is by using this formula, right. This is something that we have been doing for ages, right. I mean in our studies in high school, engineering and so on, where we just compute, you are given a set of samples and we compute the average as using this formula, and that average is actually the empirical estimate of the expectation, right. And the analogy to our derivation where we were stuck would be the following, that I am interested in the expected value of the squared error between y hat and y, and that I can just approximate from the data that I have. So, I have seen m training points. For each of those training points, I know what my y hat is, because I can pass it through my f hat x and get the answer. I know what the true y is, because that was given to me in the training data, and I can compute the difference between them, square it and take the average. So, this would be my empirical estimate for the expectation, and that is all I can do, right. I cannot really compute the true expectation, because that would mean true expectation or all possible x's that I can get, and that is not possible to do. For all the possible x's, I need to compute the y hats, also know the true y, but if I already knew the true y for all possible x's, then there is nothing to estimate, right. So, I just have a small sample of reasonable size. So, I am just going to empirically estimate the expectation using that sample, right. So, wherever I see expected value of y hat minus y the whole square, I am going to replace it by this formula. Okay. So, that is the main idea, and that is why on the previous slide I was saying that this is something that we can compute, and now I have shown you how to compute that, right. So, let us return back to our derivation now. So, this is the expectation, this is the expected error, right, the true error that we were interested in computing. I call this a true error because this is the difference between the predicted value and the true function value, right. But we do not know the true function value, so we cannot estimate this quantity, and now we have written it as a sum of 3 terms, of which I just showed you how to compute the first one empirically, right. So, now you could compute it empirically from the data, but there are 2 cases. You can either use the test data to compute this or to estimate this quantity, or you could use the training data, right. So, let us look at both the cases. So, first we will look at the case when we are looking at the test data. Okay. So, now suppose I look at the test data, then this is the true error that I am interested in. Now, the first quantity here I'm going to replace it by the empirical estimate that I just showed on the previous slide, which is the average computed from the m test points that you had, and the test points were the points from n plus 1 to n plus m. I know what the predicted value is, I know what the true value is because I was given the data as xi comma yi pairs, right. So I had these pairs, so I know what the true value is, and I just compute this difference, and this is of course easy to compute. This is expectation of epsilon square, and I just told you earlier that expectation epsilon comes from 0 comma sigma square. So expected value of epsilon square is just the variance, which is sigma square. So sigma square is going to be small, so this is a small constant that will get added here. And then you have this third quantity that you still don't know how to deal with, right. So let's just see how to deal with that quantity. So what I have written here is that this is the covariance between these two values, right, and like yeah. So what I have written here is this quantity here, I mean keeping the two aside, is actually the covariance between these two random variables, epsilon, which is the noise, and f hat x minus fx, these two random variables, and I will tell you why I am saying that, right. So you have the covariance between x comma y is E of x, the expected value of x minus the mean of x, and y minus the mean of y. Our x is epsilon, so the mean of x is of course 0, so the mean of x will disappear, and then you have y minus mu y. Now I can open up the bracket, so I get E of xy minus x into mu x, and now again the sum of expectations is the expectation of sum, so I can take the two terms out. So expectation of xy minus expectation of x into mu y. Now mu y is of course a constant, right, because you compute the expectation and then that's a constant, so that will come out. So you have exy minus mu y into E of x, but again you have E of x because x is sigma is going to be 0. So your what you remain with is E of x comma y, right. So in this case, when epsilon was a random variable with mean 0, this product between treating epsilon as x and this quantity as y is actually the covariance between these two random variables, right. So that's something that we are noting. Now how do we use this fact, what do we do with this is something that we will see on the next slide, right. So far so good. We were interested in this, we cannot estimate this, so we estimated this as a sum of these three quantities, of which the first two we know how to deal with. The third one is still not clear, right, because it again has f of x. So we need to see if we can somehow get rid of this third quantity or make some comment on that, right. So that part is still remaining. So let's look at the third part and make some observations about it. Right. So remember that epsilon here, what is epsilon actually? So y is equal to f of x plus epsilon. So epsilon is actually y minus f of x, right. So now you are trying to find the covariance, right. So this quantity, as I said, is the covariance. So between epsilon and this other random variable, and I just told you that epsilon is actually equal to y minus f of x, right. We just saw that simply comes from the fact that y is equal to f of x plus epsilon. Now the statement that I am going to make is that this y minus f of x is actually independent of f hat x minus f of x. Why am I saying that? Because when I am talking about the y's here, I am talking about the y's coming from the training data, because this expectation we are computing from the training data, right. Test data, right. So this expectation we are computing from the test data, whereas f hat of x was estimated from the training data. Your test points did not participate in the estimation of f hat of x, and these y's are actually corresponding to the test data, right. Hence these two random variables are actually independent, because the y's that you are seeing here did not participate in f hat of x, that they did not have any say in the estimated parameters of f hat x, because this belongs to the test data and the test data did not participate in the estimation of f hat x, right. So now these two quantities are actually independent. That means epsilon and this quantity is independent, right, because epsilon is simply y minus f of x, and that means the covariance between epsilon and this other quantity is going to be 0, right, because these two are independent random variables. So their covariance is going to be 0, right. So that is why you can say that in this case, when you are trying to estimate these expectations from the test data, the covariance term is actually going to be 0. Yeah, so I mean, sorry, I should have said it a bit differently. So the expectation of E epsilon comma this random variable can just be written as the product of the two expectations, and sorry, I shouldn't have said they are in, sorry. So this is correct. So the expectation of this quantity, which was what you had here, you can now, since epsilon and the other random variable are independent, you can write it as the product of their expectations, and since the expected value of epsilon is 0, you get the final answer as 0, right. So in the case when you are trying to estimate this expectation from the test data, this quantity disappears, right. So then the true error is actually equal to the empirical test error plus a small constant. So what does this mean? That if you are going to estimate the true error empirically from the test data, which is the first quantity that you see here, if you are going to estimate it empirically from the test data, then your true error is actually very close to the empirical test error. So if this is what your estimate is going to be, then you are not making a very large gap, right, because there is just plus a small constant, right. That is what we derived here, because it was a sum of this quantity plus this quantity plus this quantity. We proved that this quantity is 0, this is a small constant. So if I were to if I were to estimate the true error using the test data, then my estimation is actually very good, right. So if I compute the error from the test data, then I am actually very close to the true error, right. Now let us see what happens if we had to estimate the error from the training data. So that is why whenever you want to estimate the model, so now you have trained the model and you want to say how good the model is. It does not make sense, as I will show soon, to estimate it from the training data, because the training is always going to be optimistic, right. As you keep increasing the model complexity, it will go to 0, but your test error might still be high, and your test error actually gives you the true picture, because if you empirically estimate the error from the test data, then you are actually very close to the true error, is what we have just derived.